Okay, it is about time to start. The first presentation after the coffee break will be given by Ivan Shanshin from Corning Scientific Center, St. Petersburg. And the title of presentation is Numerical Methods of Structured Seismic Analysis.
Hello everyone again. Today I will show you my work about numerical methods of structures seismic analysis. So let's start with a short description of existing structures seismic analysis methods. The first one and the simplest one is a static equivalent static method. This method uses only a maximum acceleration from an earthquake recording, which applies to the structure as a static load. A huge drawback of this method is that it's applicable only for stiff structures, because this method, of course, don't include any dynamic effects. In most cases, we can consider structure as stiff and applicable for equivalent static analysis when the first natural frequency of the structure is above 33 Hertz approximately. Because in most cases, major frequency of an earthquake accelerogram is below this value. The second group of seismic analysis methods, it is dynamic methods. There are two main types of dynamic transient analysis. It is a model superposition and full transient method. This is the most accurate way to calculate seismic response of the structures, because any nonlinearities can be taken into account in the analysis in case of full transient method. And also, as a result, we obtain time-dependent response. But this type of analysis requires significant computational resources to be involved, because integration time step should be small enough to resolve highest frequency in earthquake accelerogram. Model superposition transient method is much more computationally efficient, but it can be applied only for linear models. And the last one, it is a response spectrum method. And the main idea of this method is to calculate responses from each natural mode of the structure and to calculate overall response using certain rule. For example, as it's shown on the slide, it is a square root of sum of squares. As you may know, response spectrum, it is a function of frequency or period, showing the peak response. It can be acceleration, velocity, or displacement of a harmonic oscillator, which is subjected to transient loading. So if we want to calculate our spectrum, we just need to apply our accelerogram of earthquake to oscillator and calculate maximum response. And if we repeat this procedure for several oscillators with various natural frequencies, we can obtain acceleration response spectrum. But in addition to whole structure seismic analysis, another important task nowadays is seismic analysis of structure components. In many cases, equipment installed inside building is subjected to significant seismic loadings, which can cause large economical losses. And significant seismic loading arises because typically structure acts as an amplifier of motion and shifter of excitation frequencies. That is, in structure, seismic motion usually has higher amplitude values. So correct seismic analysis of in-structure components requires input motion directly at the mounting point in the structure. But more often, initial seismic information is known only for a structure's base. Consequently, the problem of in-structure response spectrum calculation arises. So how to calculate in-structure response spectrum? There are two main groups of methods to calculate such spectrum. The first one is the time history method. This method implies that structure itself and equipment are treated as one system. Then we should perform transient dynamic analysis of this system and extract time history record from equipment mounting point. This procedure can give the most accurate input seismic information, but of course it is computationally inefficient due to complexity of transient dynamic analysis for large models. Moreover, time history method of calculating structure seismic input requires earthquake records, which are rarely available. And the second approach is to calculate in structure response spectrum using so-called direct spectrum to spectrum procedures, which can give spectrum in any point inside structure without using transient analysis. There are a lot of procedures developed nowadays, but in this work we will consider a procedure proposed by Vladimir Sorin in 2017. This method uses random vibration theory in its foundation. So the main goals of this study is to firstly to perform response spectrum method verification by comparing it with dynamic methods and analytical solution for simple beam problem in case of specified support motions. And the second goal will be to study Vladimir Sorin's in-structure response spectrum calculation method. So let's move on to response spectrum method verification. As it was mentioned, in addition to numerical methods, we used analytical solution based on Bernoulli-Euler beam formulation with viscous damping forces included for calculations. The corresponding beam equation you can see on the slide. Here, VET is a total displacement of the beam. As beam supports excitation, we used accelerogram sample, which you can see at the right side of the slide. And in this paper, we considered a case with when both delta 1 and delta 2 are equal. To solve beam equation, it is convenient to express beam total displacement as the sum of the quasi-static displacement Vs, which correspond to static application of the support motion, plus additional displacement due to dynamic effects. Quasi-static part can be found using the series, which is on the right down on the slide, where psi y, it is static influence functions, which in case of uniform beam are the cubic Hermite polynomials. Dynamic part of the beam total displacement can be found using standard model superposition procedure. So we just have to find natural modes of structure. So let's consider the results of calculations. On the left, you can see beam midpoint displacement. But to clearly see the difference between results, let's consider a time range from 18 to 21 seconds. And it's clear that analytical solution and numerical solution using full transient method and model superposition method are very close to each other. And in the table above, you can see that maximum values of beam midpoint displacement over time are also very close. And the most important is that response spectrum method also gives very close results to the other dynamic methods. So therefore, this method gives good prediction, good approximation for dynamic methods, and the computation time for it, it's much more is less than dynamic methods by 4 or 5 times. So it's very computationally efficient method. So now we move to Vladimir Sorin's method description. So as it was mentioned, this method is based on random vibration and response spectrum methods. So using random vibration theory allows us to calculate in structure power spectral density function, PSD, knowing ground power spectral density function, SP in here on the slide, and corresponding transfer function from ground to the point of interest inside structure. Numerically, in structure PSD can be obtained by using, for example, ANSYS mechanical APDL RPSD function. But our goal is to find in structure response spectrum by using ground response spectrum, not PSD function. So consequently, we need a procedure for direct and reverse PSD to response spectra conversion. To obtain this formula, we need to consider response spectrum and random vibration methods theory a little bit. So response spectrum method based on mode superposition technique. Thus, it is necessary to perform model analysis at first. After that, respective eigenvectors and model participation factors can be calculated. Then, using given acceleration response spectra, we can obtain corresponding model coefficient. Here, SAE, it is the value of response spectrum at frequency omega I. After that, we can calculate model response by using a formula, which you can see on the slide. And finally, total response can be obtained by using one of the mode combination methods. Random vibration method uses power spectral density function instead of response spectrum as input. It also based on model superposition technique. The main difference between these two methods is in the output. In response spectrum method, we obtain deterministic maximum response of the structure, while and for harmonic oscillator, square of standard deviation looks like this formula. But if our excitation has the form of smoothly varying function and the damping ratio is low, we can use this approximate formula. So after all, we can obtain model coefficient for random vibration method. And as you can see, we have two expressions for model coefficient, and to calculate, to obtain response spectra, PSD to response spectrum conversion formula, we can just equate these two expressions, and after that, we can obtain this formula. Also, as you can see, it is an integral equation, so we can solve it regarding to variable SP. And after that, we can obtain inverse formula for conversion response spectra to power spectral density. Here, I want to put two comments. First, this equation is obtained using approximate formula for acceleration standard deviation, as it was mentioned before. And this formula is valid only for broadband smooth spectra and for low damping ratios. But in structure PSD can have sharp peaks for the structure natural frequencies, at the structure natural frequencies. Thus, it is recommended to use exact equation for standard deviation in such cases. And after corresponding calculation, we can obtain this formula. So summarizing all above mentioned information, we can formulate Vladimir Sorin's structure response spectrum calculation algorithm. So the first step is to calculate PSD from input spectra using this formula. After that, we should calculate PSD in the point of interest inside structure. And after that, we can calculate corresponding response spectrum using one of these formulas. This is approximate, and this is an exact formula. So let's consider a test problem statement. So method performance was investigated on a beam problem, similar to first part of this article. So right base of the beam is subjected to same seismic excitation, and we calculated in structure response spectrum at the beam midpoint. For comparison purposes, we used a solution using time history method for of in structure response spectrum calculation, which was described in the introduction. Corresponding response spectra for damping ratio equal to 5% looks like this. So as we can see, main peak of the input accelerogram corresponds to 4.3 Hertz frequency. Beam first natural frequency was chosen equal to 4.5 Hertz to consider method performance in near resonance conditions. Corresponding PSD function you can see on the right side of the slide. So as you can see here are some sharp peaks. So using approximate formula here is doubtful. And as we can see later, this formula can give wrong results. So this is the results of calculation. We considered a few values of damping, 2.5%, 5%, and 10%. Results for the first damping ratio is on the left. As anticipated, approximate formula gives wrong results. So we can see serious overestimation of peak acceleration comparing to exact formula and time history method. But exact formula gives a good approximation of the peak value, and overall performance of the method is acceptable. The same situation for second damping ratio, but the peak value for approximate formula is a little bit better. The last damping ratio, results for the last damping ratio is on the left. So as you can see, results for approximate formula have improved a little bit more, but it's still, but the error is still quite serious. And as we can see in the table on the right, the error for all three cases for exact formula is above 8%. So if we are using exact formula, we can achieve a very good approximation to solution using transient method. So in conclusion, I want to say that in this work we compared basic seismic analysis methods, full transient, mode superposition, response spectrum on a simple beam task, and in addition we performed an analytical solution. Results showed a good agreement between all methods. Then a new method developed by Vladimir Sorin was described and investigated. Two separate approaches were used. First uses approximate formula for acceleration standard deviation, and second uses exact formula. It was showed that approximate formula gives overestimation of structure response spectrum peak acceleration, but exact formula gives a good approximation. So that's all. This is a list of references. If you have any questions, I'm ready to answer on it.
Yeah, thank you very much. It's I have a you probably can apply this analysis to maybe to apply that to development of active seismic protection. Yeah, something like Professor Lin was telling us in his keynote lecture, and maybe this analysis can be employed to predict more efficient parameters for active seismic protection. Am I right?
Yeah, of course, but maybe we should perform some more tests on bigger models, maybe with a lot of degrees of freedom to understand how this method works on big structures. But yeah, I think this method should give good results in this case too.
Very interesting. Questions, please.
We got a question here from Alexander Dutchenko.
Yeah, please. We have. Okay. Yeah, Alexander, you can now.
Okay, you can hear me. Thanks a lot. So my question relates to the comparison with a nonlinear analysis. I mean, have you compared your results with the results including plasticity and viscosity with structural elements? I mean, for example, have you performed computations for structural models using your approach and structural approach, including not only damping but also plasticity for the elements?
Yeah, I understand the question. Unfortunately, response spectrum method is applicable only to linear structures, so non-linear effects cannot be taken into account because here we should perform model superposition procedure, which so
Yeah,
we can't perform this procedure for non-linear model, unfortunately.
yes, I understand that, but my question was, have you tried to take nonlinear effects into account?
Yeah, okay. No, we have not tried yet, but
Thank you.
yeah, but maybe in future we
Thank,
will try.
thank you very much. Thank you.
Thank you.
Thank you for
More
question.
questions? We have time for more questions because we got a slight problem with two following presentations, so we can use a little bit more time for that presentation if there are more.
Can I have question?
Yeah, absolutely.
Thank you for your presentation. I have one question. Suppose the wave travels from beneath of the from foundation to the superstructure.
Mm-hmm.
Then, say first, second, or anyone else shock will destroy the structure before actually vibrations will occur. How to accommodate that kind of fracture before vibrations? Do you know the answer?
Maybe I don't know, but I can try. The problem that we are studying here is when the structure itself has a good seismic performance, so we consider that structure will not be destroyed by earthquake, but the equipment inside it is maybe fragile and due to amplification of seismic motion due to some effects of resonance and other, the equipment can be how to say it properly. So the loading for equipment can be much higher than for foundation of the building, and that problem we try to solve. So we don't solve the problem when the structure itself are destroying by earthquake. So
Thank you.
thank you for your question.
Yeah, more questions? We still can accept additional questions.
Can I ask another question? Could you please clarify whether your work targeted to construct spectrums, for example, for each floor of a structure, rather than for the whole structure to estimate its equilibrium and strength?
Yeah, this work is more for, as you said, floor spectrums. So it is a serious task in seismic engineering to calculate floor spectrums, and this method can do it very fast and without transient analysis.
Yeah, thank you. I get it.
Thank you for your question.
Yeah, any other question? Okay, then we thank the presenter once again for this very interesting presentation, and we can proceed further.